Alright, let's talk about horizontally launched projectile motion. Now first off, if we want to define a projectile is anything that once projected, propelled, thrown, kicked, etc. is solely under the influence of the force of gravity. So by definition, a projectile is in a state of free fall. So it doesn't matter whether you're talking about dropping a ball off the cliff, or tossing a ball straight up in the air, or tossing a ball at an angle. Right? All of those are projectiles. They're all under the sole influence of the gravitational force. And their acceleration, right, is an acceleration that is caused by the force of gravity. So in order to understand how to look at projectiles, we first want to look at the most basic type, which is your horizontally launched projectile. So let's pretend for a minute that we had ourselves a magic switch that could turn on and off the gravitational force. Right? If we were to have this cannon up on a cliff that is going to fire a horizontal projectile, right? A projectile traveling solely in the horizontal dimension, right? And you turn gravity off, well, what would happen? Once it's projected, right, it would follow its inertial path. Now, notice, if each one of these images represents, a second passing, what's true about the distance covered in each time interval? Well, the distances covered are the same, right? Which means that in the absence of gravity, this cannon travels at a constant speed in a straight line, right? So it's got a constant velocity, right? And this thing would never come down. It would continue in this direction at a constant speed forever because there is no horizontal force acting on it. Right, again, we're considering air resistance negligible. Now what happens if we turn gravity back on? Right, notice this horizontally launched projectile will eventually come crashing to the ground. Well, why? Because there is the force of gravity acting on it. Now one thing to consider though. Notice if we look at the horizontal position of the cannonball at those same times. Right, what can we say about it? Well, horizontally speaking, there is no difference in the motion whether gravity is turned on or off. Right? So if we're only analyzing the horizontal motion of this cannonball fired off the cliff, there is no difference whether gravity is on or off if we're just analyzing the horizontal. Well, why is that? Well, think about your components. Having gravity on means that you have acceleration due to gravity on. Well, your horizontal component of velocity, we'll call it v sub x, is horizontal, right? And what dimension does your gravitational acceleration exist in? Well, vertical dimension, right? And as we talked before when we were talking about vector quantities, a vertical vector has no influence on a horizontal one. They don't coexist at all in any dimension, and so your vertical acceleration does not affect your horizontal velocity, right? So horizontally speaking, this cannonball continues at a constant velocity, at a constant speed. Now, what happens vertically? Let's go ahead and plot our vertical position all in a line. This motion diagram should look really familiar to you. What's happening in the vertical? Well, you've got an object that is solely under the influence of gravity, so it's in free fall. So horizontally speaking, you've got an object traveling at a constant horizontal speed, whereas vertically speaking, you've got an object that's in free fall. Right? And you've got to analyze the two dimensions separately. Now, one interesting experiment we always do is you consider, is there a difference between, say, dropping a bullet and firing a bullet horizontally? Which one will hit the ground first? Well, and the answer is they hit at the same time, right? Because again, it doesn't matter if it was fired horizontally or just dropped. Vertically speaking, what's the initial velocity in the vertical dimension for both objects? Well, the vertical initial velocity for both objects is 0. Do they fall the same distance? Yes. Do they have the same vertical rate of acceleration? Yes, 9.8 meters per second squared. So in the vertical, there is no difference between dropping it and firing it horizontally. They'll both hit the ground at the same time. Now I'll also include a link to the Mythbusters doing it. It's a pretty cool experiment. But we can also do it here with this thing. Now, hopefully you can see that okay. What this guy's going to do, whoops, I'm going to cock it. Now I'm going to put one ball over here. And I'm going to put the other ball right here. Now when I flip this, right, the spring is going to expand. This one will be fired off horizontally and this one will be dropped. Now obviously you won't be able to see them hit the ground, not with this camera, but you can't really see it in person. So what I always tell the people in the in-person class to do is listen for it. You should hear one sound as they hit, right? So they should simultaneously hit the ground. So you just want to listen for it, and hopefully the audio is fine enough to where you can hear it. Right, so that first clank, before you heard the other one bouncing on the table, right, was both of them hitting the ground simultaneously. Right, because again, they both start with a vertical velocity of 0, they both fall the same distance, and they both have the same acceleration. So let's take a look at what this might look like. Well, first off, let's go through what's happening in the horizontal and the vertical. Now, in the horizontal, you've got no forces present, therefore no acceleration, therefore your velocity is constant. Whereas in your vertical, you do have a force present, you've got gravity. You've got an acceleration that is due to the force of gravity, and so you have a speed that will be changing. So let's take a look at a concept question together before we get into the math. Let's say we got two balls. They're rolling towards the edge of a table with ball 2 rolling twice as fast as ball 1. Both balls leave the edge of the table at the same time. Which ball hits the ground first? Which ball goes further? So pause it, think about it, then resume. So both balls roll off the table. Right, if we were to sketch this out, ball 1 and ball 2 both roll off the table, right, horizontally. So they both have an initial vertical velocity of 0. They both fall the same vertical distance, and they're both under the same gravitational acceleration. Therefore, they've got to hit the ground at the same time. Now, which ball is going to go further? Well, if we look in the horizontal is at, or is in constant velocity, right? So v sub x is equal to x over t. Well, the time for both of them is the same, so whichever one is going faster in the horizontal is going to go further, right? So because ball 2 is rolling twice as fast, it will go further than ball 1. But they will both hit the ground at the same time because vertically speaking, their motion is identical. Alright, so let's say in this example, we've got a 100-gram ball that rolls off a table and lands 2 meters away from the base of the table. A 200-gram ball rolls off the same table with the same speed. How far does it land from the base of the table? So again, pause it, think about it, then come back when you got an answer. Now think back to when we were discussing free fall, right? Because both of these balls, vertically speaking, are in free fall. Did mass ever make a difference? No, right? The gravitational acceleration is independent of the mass. So the 100-gram ball, if it goes 2 meters, so will the 200-gram ball. right? Because again, mass does not matter here, right? Mass is none of our formulas so far, right? The only thing that matters is that gravitational acceleration, and that gravitational acceleration is identical for both objects. So let's go ahead and look at a mathematical example together. Let's go pull up a random one. Okay, let's say we've got someone who leaps from the edge of a cliff with a horizontal velocity of 3.3 meters per second. He hits the water 1.2 seconds later. We want to know how far out does he land and how high is the cliff. Alright, so let's sketch out our scenario. We've got a guy who leaps directly horizontally out. He has an initial velocity in the horizontal of 3.3 meters per second. We want to know how high this cliff is and how far out he lands. So notice we've got two different distances now. We've got a vertical distance and we've got a horizontal distance. And the time it takes for him to hit the water is 1.2 seconds. Now before we jump into solving this, it would help to look at our equations. Now in the horizontal, you have no acceleration. Right? So in the horizontal, you only have one equation. That your velocity is constant and your change in position over your change in time equals that constant velocity. Now in the vertical, we can go through our three kinematic equations and just adapt them for the vertical. So your final vertical velocity is equal to initial plus acceleration due to gravity times time. Your final vertical velocity squared is equal to your initial vertical squared plus 2 times acceleration due to gravity times your vertical displacement. And lastly, your vertical displacement is equal to your initial vertical velocity times time plus 1/2 of g times time squared. Alright, so we're working with all equations that are familiar to us. We're just tacking on subscripts here to differentiate between the horizontal dimension and the vertical dimension because, again, they do not coexist at all, so we have to treat them separately. Now, this is a vertical launch, right? Or sorry, a horizontal launch, right? If you have something that is launched perfectly horizontally, we know that our initial vertical velocity is 0 because there is no vertical component to a horizontal velocity vector. So now we've just got to piece through these equations and find out what we're missing. So if we want to find x, that distance that he lands away from the cliff, we're also going to call this the range a lot in problems, right? Like when you talk about the range of a rifle, you're talking about how far that rifle will shoot. So we know that our horizontal has constant velocity, and that constant velocity is 3.3 meters per second. We want how far out he goes in 1.2 seconds. Right, so 1.2 times 3.3 gives us a range of 3.96 meters. Alright, so we found how far out he goes. Next, let's look at the vertical. Because if we want to find a vertical value, we can only be using vertical variables. Now notice the only variable that coexists in both dimensions is your time. Alright, so we got v naught y. We got y. We know the acceleration in the vertical is g. So we could use y equals v naught yt plus 1/2 gt squared, where our unknown height is equal to 1/2 of g, negative 9.8 meters per second squared, times 1.2 seconds squared. And so we get a vertical displacement of 1.2 squared times 9.8 divided by 2 of 7.1 meters. And it comes out negative because the displacement is a downward displacement. Alright, so really, we're still using the same three kinematic equations and the equation for constant speed. It's just we have to keep our dimensions separate, right? Vertical variables can only play with other vertical variables. Horizontal variables can only play with other horizontal variables. The only variable that crosses dimensions is time. So in the next video, I'll be showing you how to deal with projectiles if they are launched at an angle. The same general idea, it's just now we're adding in some more trig. So, see you next time.